This is another new part of the specification for 2017. So as well as knowing what a capacitor is and how they work in circuits, you now need to understand the capacitance formula, which is about how you can actually determine what the capacitance of a capacitor will be from its physical dimensions and the material it's made from. So here's a little picture of a capacitor. We've got metal plates, and there's this material we'll talk about in a minute called a dielectric that goes in between them. This is a wound capacitor, but they only talk about parallel plate capacitors because these are a little bit more complicated, but the same principles apply as long as you're thinking about a metal plate, some material separating that from the other plate, and a second metal plate. So one of these plates will end up being positively charged and the other one negatively charged. Okay, so if you think about what's going to affect the ability of the capacitor to store charge, the area of the plates will make a difference, the separation of the plates will make a difference, and the nature of that dielectric material that goes in between them will also make a difference. And what we need to think about is what effect will changing each of these three variables have. So if we think about why the capacitor stops charging, so let's suppose I apply 1 volt of potential difference to this capacitor, and we're thinking, okay, how much charge will it store? Well, the first thing we need to think about is the area of the plates. And the capacitor stops charging because there's an electric field creating a force which pushes these charges onto the capacitor, these electrons, but they start to repel each other. Obviously, the closer they are, the stronger that force of repulsion. So if you think what's going to happen here, eventually, even though there's a field pushing these electrons onto the capacitor, they're repelling each other, so no more get on. And if I increase the area of the plates, these electrons will be more spread out, so I'll be able to put more electrons on before the force between the electrons of repulsion stopped any more getting onto the plates. So the bigger the area of the plates, the more charge can be stored at the same potential difference, i.e. the bigger the capacitance. Okay, I haven't gone to show that's proportional, but you can see certainly, hopefully, if you increase the area, you will increase the capacitance. Okay, but then we need to think about, of course, a capacitor. Before I just had 1 plate there, but real capacitors, of course, have 2 plates. So what happens is, if I change the separation of those plates, well, when I put the electron onto this plate, it pushes an electron off the top plate, leaving a positive charge behind. So as I put more and more electrons onto the plate, I get a more and more positive charge on the other plate. Well, these positive charges are pulling more electrons on, so although this electron's being repelled by this electron, it's being attracted to the positive charges left on the opposite plate. So the closer these plates go together, the more attraction there is pulling the other electron. Okay, so hopefully you can see from that moving the plates closer together will make it possible to get more electrons onto the plate. Okay, to summarise that, the capacitance is inversely proportional to the separation of the plates. The closer I put the plates together, the more charge can be stored. So if we think about that and just take that a little bit further, the positive charge on this plate is attracting the negative charge on this plate. But if I put a material, this dielectric material, in between the plates, what I'd really like it to do is to transfer that electric field better. Okay, so if I just had a vacuum or empty or air in between these plates, the electric field would pass. But what I really want to do is to increase, okay, how well that electric field is transmitted. So the way how well a electric field gets through free space normally is called the permittivity of free space. Hopefully you've come across this number in electrical fields, and we can increase this by a relative permittivity, which is just a ratio. So this number you'll know is 8.85 times 10 to the minus 12, but this number, the relative permittivity, just says how good the material is, how many times better it is than free space. So that number might be like 2 or 5 or 10, to say it's just 10 times better than an empty space at transmitting the field. The better we transmit the field, the more charge we'll be able to store. Okay, so the capacitance is proportional to how well that field's transmitted across the gap, okay, which is the relative permittivity times the permittivity of free space, epsilon 0 times epsilon r. Okay, well, how do we do that? Well, here's a dielectric material, it's got a polarized molecule. So this molecule has got a positive end and a negative end, and what happens is when the electrons come onto the bottom plate, they cause the electric field in this polar molecule, this dielectric, to rotate. And you can see there that the positive parts end up near the negatives end up near the positives, so that means that the electric field is transmitted better across the gap, and therefore the better this dielectric material is at rotating and transferring this electrical field, the more capacitance the capacitor will have. Okay, that leads us to the overall summary formula, which is the capacitance of a capacitor is the permittivity of free space times the relative permittivity of the dielectric material times the area of the plates divided by the separation of the plates. Okay, now if you look at this formula, you might think, well, I've got to make A bigger and bigger and bigger to get a bigger capacitance, but why don't I just make D smaller and smaller and smaller? If I could make D incredibly small, then I could end up with a huge capacitance without having to have a big area. But of course you run into a problem, and the problem is that eventually the electrical field across the capacitor becomes so big that you break down the molecules there and you get a spark, and then of course as soon as charge flows through a capacitor, it's no longer acting as capacitor, and that's not then going to store any charge. So just a couple of quick questions. If you've got a 20 by 30 centimeters piece of aluminium foil and some paper, and the relative permittivity of the paper is 2.5 and it's 0.1 millimeters thick, what's the highest value capacitor you could make? Well, how are we going to do this? We're going to have to cut this capacitor, this foil in two to make two plates. So the capacitance is going to be the permittivity of free space times the relative permittivity times the area. Well, this is 20 by 30, so 600 centimeters squared, but we need half for each plate, so 300 centimeters squared, 10 to the minus 4 there to convert the centimeter squared to meter squared. Here's a separation of the plates, 0.1 times 10 to the minus 3 meters, gives you a capacitance of 6.6 times 10 to the minus 9 farads. How will it break down? How many volts? So what will the voltage rating of this capacitor be? The maximum voltage you can apply. Well, the electric field is V over D. So the voltage that I can apply to that is the electric field strength. The maximum electric field strength I can create times the separation, 2 times 10 to the 5 times a separation of 0.1 millimeters gives you 20 volts. So this capacitor will be rated as 6.6 nanofarads, 20 volts. Any more than that, you're going to ruin your capacitor. What's the maximum charge you could store? Well, that's just Q equals CV. So the capacitance times the voltage, I could store 1.3 times 10 to the minus 7 coulombs of charge, and there 130 nanocoulombs of charge.